And comets will be only part of the story, but I think an important part. So, let me start by showing you a brief introduction to how much water we have on Earth. As you know, more than 70% of the Earth's surface is covered by water. So we have a lot of water in the oceans. And if we estimate the mass of this water reservoir, it comes up to about 1.5 times 10 to the 21 kilograms. But that's not all the water we have in the Earth. We don't know very much about the water in the Earth's interior. But there is some water there. We have good evidence for that. And it's generally estimated that we could have a couple of additional oceans in the Earth's mantle. And if we take that into account, we could estimate the total amount of water in the Earth to be about 6 times 10 to the 21 kilograms. That's a figure with a large error bar. We don't know very accurately, but it's generally estimated.
Wait a minute.
Something like that.
How can you hide that kind of water in the crust?
Not the crust, it's mainly in the mantle.
In the mantle?
Yes. So the mantle rocks are not completely dry. Don't ask me any details about that. I'm not a geochemist, but that's what I've been told. Maybe some of you knows more.
Yeah, I was a chance there. Can you comment on that? How could that be such amount of water in the mantle?
Is it crystal water or is it chemically bound?
I'm not sure, but it's supercritical water, and it's part of the fluids, some of the other fluids inside there. So quite maybe. It's a big crystal water.
I also have the impression that these two reservoirs, if you like, the oceans and the mantle water, are not completely separated, but they have been in contact during the Earth's history. So it's really the same water. Now, if you compare this number with the Earth's mass, it turns out that this is about 1 per million of the Earth's mass. So it's an amount of a volatile substance that we somehow need to explain how it got into the Earth. And there are some standard pictures of the origin of the Earth's water that I summarized here. I think that in a way this terminology may rather be confusing, so let's not take it too seriously, but just to tell you the background. One idea has been that the water could be so-called, so to speak, endogenous, that is, intrinsic to the Earth's material, the local material from which the Earth accreted. So it's local water acquired from the solar nebula near the Earth's orbit. So that's one idea. Another idea could be called asteroidal water, and that would be water that was somehow brought into the growing Earth while the Earth was accreting from a region somewhat further out, the asteroid main belt. The third idea is that of cometary water. And when people are talking about cometary water, traditionally, they will mean water that came into the Earth very late, when the Earth was already full grown. And say, even the moon had formed by this giant impact. And after that, water came via comets into the Earth. So that would be a late veneer in the traditional sense. But the story that I will tell you today will somehow mix these topics these ideas with each other. So, okay, we will see what I mean with that. So let me start with a discussion of this local water. And there is a strong argument against this endogenous water that can be illustrated by this diagram here. This diagram is an old diagram. It shows results of calculations of chemical equilibrium. If you take a solar nebula, that is the gas disk that preceded the planetary system, put it at high temperature so that all the elements, you have a solar composition of elements, all the elements are in gaseous form, atomic form, and then you cool the nebula, you form molecules, you form these gas molecules go into the solid phase at some typical temperature, and you form solid compounds. And the staircase in this diagram shows you the limit between gaseous and solid phase, where most of a certain element goes into the solid phase, which temperature that occurs at. And to the right you have the most refractory elements that go into solids at very high temperatures. To the left you have the volatiles that stay gaseous mainly until the temperature has decreased very far. And you see that H2O, ice, is formed at a temperature of somewhat less than 200 Kelvin. Typical meteoritic minerals like pyroxene and olivine are formed at temperatures around 500 kelvins. Enstatite, like you have in some meteorites, even higher. And the argument here, which could be used against the idea of local water in the Earth, is that in order to build a planet you need only solid material. And therefore you could sort of compare the solid materials that you see in this diagram with what we find in meteorites, because we know that the meteorites come from the asteroid belt. And if you do that, you can sort of read off here that the temperature in the main asteroid belt should have been around 500 Kelvin, because that seems to be the temperature where you condense those compounds that the meteorites consist of. So that was a fairly high temperature at that distance from the sun. And then the Earth formed inside. And how could you, under such circumstances, expect to get any water ice into the Earth? It's just impossible. You could get some water into minerals at somewhat lower temperatures than the typical meteoritic temperatures. You get some hydrated minerals like serpentine at somewhat lower temperatures, and you find those minerals in some of the meteorites that come from the outer part of the main belt. So there, apparently, you could have incorporated some water into the minerals that formed there. But again, at the Earth's orbit, you wouldn't expect any water to be present in the solid phase. So that's a very simple argument that has made people think that the water should have come from somewhere else. Now, we have evidence of water. Let me show you some of it in the asteroid belt. This is a diagram showing the semi-major axis of the asteroid orbits from 2 AU here to 3.5 there, and the main belt is situated in that region more or less. And what's plotted here is the percentage of observed asteroids that have shown a certain spectral feature at 0.7 microns, which is interpreted to be a transition of iron in hydrated minerals. So that's a sort of proxy for water content of the rocks. This comes from a paper in Protostars and Planets 5. Have any of you seen that book yet?
Yes.
It has appeared.
Yeah.
Good.
The map is.
So maybe it should be 2007. So this diagram shows that a substantial fraction of the asteroids have shown the presence of those hydrated minerals. So there is some water in the rocks in the asteroid main belt, although one sees that the fraction really grows with distance from the sun and higher in the outermost asteroids. In the inner part of the main belt, you practically see no water at all, and that's interesting. Another recent finding that is a complete surprise to everybody in this field was the discovery of a comet in the midst of the main asteroid belt. It's the top diagram here, the top picture showing Comet Elst-Pizarro, which was discovered some 7 or 8 years ago, perhaps 10 years. And that is an object that has an orbit just like a main belt asteroid, in the outer part though. But it's a main belt asteroid orbit, and it's a comet. Clearly, it has a tail. And nowadays there are 3 comets identified in the outer main belt. You see all 3 in these pictures. So what does this show us? It shows us that there must be some subsurface ice in these asteroids that somehow gets exposed, perhaps due to a collision or something, and the ice starts to sublimate. Slowly, but you get some cometary activity. These asteroids are situated at around 3 astronomical units. It's the outer part of the main belt. And they belong to one big collisional family called the Themis family. So maybe the parent object of this Themis family had a lot of water in it, water ice. Now, this, as I said, was a complete surprise when the first discovery was made. But actually, there are dynamical routes that could link the main asteroid belt to the cometary population. So it's not impossible. And such dynamical routes from the Jupiter family, which is a typical cometary population, into the main belt exist, and they could have been even more efficient when the gas disk existed, the solar nebula, in the very early, just the beginning of the solar system, as we shall see. So there is water in the asteroid main belt.
Has the water been detected, or is this an assumption you are making?
Well, I don't think anybody has detected the water molecule in these 3 comets, but probably OH has been seen.
Mm-hmm.
And so it's cometary activity. It's not something completely different. And then we have these hydrated minerals, as you saw, which is again indirect evidence.
Mm-hmm.
But we have some more direct evidence from meteorites, especially carbonaceous chondrites. The picture here shows the Allende meteorite, which is the most famous, one of the most famous carbonaceous chondrites. Those chondrites, they consist of a mineral mixture that has the lowest formation temperature compared to the other kinds of meteorites. And we think that they come from a class of asteroids which we call sea asteroids, which are spectrally similar to those meteorites. And those sea asteroids are dominating in the outer part of the main belt. So these carbonaceous chondrites, we believe that they are samples from sea asteroids, typical of the Themis family, for instance.
Is the water bound as some sort of crystal water there, or how is it?
That's a good question. I would like to learn more about carbonaceous chondrites. Actually, it's for sure it's hydrated minerals, hydrated minerals like serpentine and so on. But there could also be perhaps some crystal water in the rocks. There is one particular feature about carbonaceous chondrites called aqueous alteration. So one can see structural features in these meteorites that prove that liquid water has flown through cracks, pores in this rock once upon a time. That's clear. Not condensation of vapor from the solar nebula, but liquid water ran through these rocks once upon a time. I think that's fairly interesting, because it seems then that not only did we incorporate gaseous water from the solar nebula into the rocks when they were formed, but apparently there also came ice, which melted somehow. These carbonaceous chondrites, perhaps surprisingly, contain quite a lot of water, up to about 10% water as clay minerals and serpentines. Okay, there you have a sort of answer. And that's a fairly high fraction of water. It's variable. Some carbonaceous chondrites contain much less, but up to about 10% exists. Compare this now with the other kinds of chondrites. The ordinary chondrites and the enstatite chondrites, they are very dry. Say perhaps up to 0.1% water, which is like the Earth, or less. And those come from the inner main belt. Many of them are completely dry, as far as we can see. So, again, this seems to imply that the original material that formed at different distances from the Sun was very dry at the Earth's location, and also very dry in the inner part of the asteroid main belt. But somehow, quite some amount of water came into the materials that were formed somewhat further out.
Can we be sure that this is not contamination? I mean,
don't ask me. I'm not a meteoriticist, but
of course, but I'm thinking of, for instance, there are minerals that really suck stuff like zeolite, that things, and that you have to heat it a lot to get rid of it.
In any case, this is something that you only find in carbonaceous chondrites, not in other chondrites.
Since you're taking questions, I was a little bit surprised in the very beginning that you are having a temperature of 500 K at the distance of 3 AU.
Yes.
Now, I have some energy problems there in the disk. How do you see upon that? How natural is it for you to assume this high temperature then?
I think that when the disk was turbulent and you had inflow, then you might well expect such high temperatures. Later on, when the turbulence subsided, I don't think that you would expect such high temperatures there. That's all I can say.
I'm not aware of any theoretical model which would yield these kinds of temperatures at this distance. Therefore, it's interesting, but I don't get this together.
Even in an active viscosity.
Yeah, you need an enormous viscosity in that case. Maybe during short times, maybe during FU Uranus.
Okay, let's say that.
Is that okay? With short,
maybe
short periods of
but
time.
Also, I think that the actual temperature could well have been a bit lower, only not low enough to form the other sorts of things that would come at lower temperatures like water ice and so on. If you only see those minerals that formed at 500 K, and then you could have had a temperature of only 300 perhaps, and no other minerals would come and show up at that temperature. That would also be possible.
And this brings me to the second part of my question. Why do you have to assume that the solids are actually formed there, that they have not been there from the beginning, from the pre-solar nebula?
Yeah. Well, in the case of comets, it's a popular idea that their material is actually pre-solar, that we have pre-solar ice that just never melted. Even perhaps didn't even crystallize. That's also popular thought. But then we're talking about larger distances, and yes, for sure, we have pre-solar grains in meteorites as well. We have silicon carbide and things like that. So it's not only material that sort of vaporized and condensed in the solar system, for sure. The diagram I showed before is a sort of old picture that people had in mind like 30 years ago. We know better.
Okay, sorry.
So the argument regarding the endogenous hypothesis was rather that the Earth would have become too hot during its formation rather than that the solar nebula at this location was too hot. Or was that actually also a problem?
Yes, that's also a problem, that the solar nebula likely was far too hot to condense water ice.
But again, if the critics are right, then it may have been cooler both at 3 AU and at 1 AU, of course.
Yes. In a sense, yes. But then we have to go to the meteorites and see that those that come from the inner part of the main belt are very dry. So that's a sort of observational item which is important. But actually, the location of the snow line is one of the important questions that are still open. And I will come back to that later on. So, let's look at some geochemical data. One particular item that is discussed very often when we talk about the origin of the Earth's water is the deuterium to hydrogen ratio. And this is a diagram that summarizes some measurements of that. You have the Earth here, and this value here of D over H is the value that characterizes the Earth's oceans. To the left, you have a plot of comets and meteorites. And you see 3 comets there: Comet Halley, Comet Hyakutake, and the Comet Hale-Bopp. Those are 3 recent, fairly recent, bright comets where measurements have been made. And in Comet Halley we have the in situ measurements by spacecraft. You have a very small error bar. Hyakutake and Hale-Bopp were observed by remote sensing, larger error bars, but the points actually agree fairly well with that of Comet Halley. And these authors have indicated a very narrow range there for cometary D over H values. Now, I personally think that you have to take into account the width of these error bars and rather consider that there could be a wider range of cometary D over H values than these people seem to think. But it's still, from the few comets that we have observed, it's remarkable that they are fairly close to each other anyway. And compare that with the meteorites. You see here the fairly wide region of carbonaceous chondrites. So the water in carbonaceous chondrites, in different carbonaceous chondrites, spans a wide range of D over H ratios. So what could that mean? Maybe that the water in different carbonaceous chondrites came from different places. It's at least one possibility. There is also one ordinary chondrite plotted here. It's called LL3 there. It's an LL chondrite. It's low in iron and low in metal. And some measurements have been done in different parts of that meteorite, and they span a wide range as well. So these meteoritic ratios of deuterium to hydrogen, they span actually they enclose the value for the Earth's oceans, but they span over a wide range. So it's possible to think that the Earth's water could have come from asteroids, from via meteorites, if you just take the right mixture, so to speak. But it's also possible that some of the water could have come from comets, of course, although not 100% if you believe in those numbers. We can also see that for planet Mars, the d over h is somewhat higher than for the Earth. We have one measurement for the Martian atmosphere here, and then we have Martian meteorites. And they all are a bit higher than that for the Earth. Now, what can we do with this? I just wanted to show this because it's discussed so often. I don't think that one can draw very firm conclusions at all from this. It appears that the Earth's water could be a mixture of cometary and asteroidal water, as I said, and possibly even with some endogenous contribution, which would correspond to the protosolar value, which we see here. You could even imagine that we mix in some of that water.
So one question, how do you determine whether a meteorite is on Mars or not?
That comes from partly, well, the most important is that the abundances of different gases measured in these meteorites is in exact agreement with the abundances of gases in the Martian atmosphere.
In the atmosphere.
In the atmosphere, yes. And then we also see that the crystallization ages of these meteorites correspond to what we could expect from Martian rocks, not from meteorites. They are much younger, and they are not as young as most terrestrial rocks. Now, there are some things some problems that one has to bear in mind here. The cometary deuterium ratio has been measured for these three comets, and they are comets that came from the Oort cloud. Now, what does that mean? It means that dynamically they should have come once upon a time from what we call the scattered disk. It's part of the trans-Neptunian population, which is in contact with Neptune and is being gravitationally scattered by Neptune. So these comets came from that population. And it's possible then that if some comets brought water to the Earth, that could have been a different kind of comets, perhaps. Perhaps like the comets in the classical Kuiper belt, or something else. So it's not sure that the comets that we are interested in, from the point of view of the Earth's water, belong to the same population as these three observed comets that we have now. So this is one thing one has to bear in mind. Another problem here is that the deuterium to hydrogen ratio could be modified at sublimation, during sublimation of the ice. So maybe an H2O molecule could sublimate less efficiently than an H2O molecule, or diffuse at different efficiencies through the porous matrix of the cometary nucleus. So there could be some fractionation related to the outgassing from the cometary nuclei. So that would mean that perhaps the D to H ratios that we measure in these comets might not be representative of the nuclear material. Let's not bother too much about the Martian ratio. This was higher, as we saw. It might have been raised by atmospheric erosion, like we see for Venus. For Venus, we know that H2O was gaseous in the atmosphere once upon a time, and then this H2O was photodissociated by sunlight, and the H atoms escaped much more efficiently than the D atoms. So therefore we have a very high D to H ratio for Venus. Some of that could have happened also for Mars, because apparently at some time most of the Martian water might also have been in the atmosphere. Another piece of evidence, I think it's rather interesting, is the one of the noble gases. So here you see abundances of neon, argon, krypton, and xenon. It's plotted for Mars, Earth, and Venus, and then you see the patterns of H chondrites and C chondrites, ordinary chondrites and carbonaceous chondrites. And you see the solar pattern by the dashed line there. If you compare these, you can see that krypton over argon in the Earth and Mars is much larger than the solar ratio. While it appears to agree with the chondrites. But then if you look at xenon over krypton, in both Earth and Mars, it's much less than the chondritic, while it appears to be more solar. So it doesn't fit exactly with any source of noble gases directly. You might think that the noble gases came from the solar nebula, then you would have solar ratios. You might think that they all came from chondrites, then you would have the chondritic ratios, but it doesn't fit. And there is an idea about this. Toby Owen and Akiva Barnun came up with this more than 10 years ago, that the Earth's noble gas ratios could be explained if you make a mixture of first rocks, terrestrial rocks, that have no noble gases at all, and then a source of noble gases which you represent by cometary ice. And this cometary ice, according to them, would be amorphous ice. Amorphous ice is an ice that you can form by condensation at very low temperatures, and which forms a very fluffy porous structure where you can trap gases if those gases are present when the ice condenses. And if you condense such amorphous ice at a temperature of about 50 Kelvin, you would find, according to their experiments, that the noble gases are trapped in exactly, more or less, the ratios that we observe for the Earth and Mars. So their idea was that we could have a cometary contribution here of volatiles to those planets. The caveats to keep in mind here are, on one hand, that this was just an idea based on laboratory experiments, and the idea that cometary nuclei consist of amorphous ice, not crystalline. Observations were lacking, and they are still lacking. We do not have observations of cometary ratios of noble gases. It's too difficult. It's been attempted, but we don't have enough data yet. So we don't really know, and we also don't know what the cometary formation temperature actually was. We have some indication from the ratio of author to para water in comets that appear to indicate a formation temperature of about 30 Kelvin of that ice. But so it's difficult really to conclude anything from this. Let me not go into this argument too deeply now. We will come back to it later. Now, what time did I start? Is it 10? Yes. So then we can break in 5 minutes or so. Let me show you some arguments that were put forward in a recent review paper by Michael Drake and Roberto Campins. They are proponents of the endogenous water idea. And one argument that they bring forward in favor of the endogenous water is the fact that water existed on the earth very early in its history. Very early. So there is evidence for an early H2O ocean from the xenon isotopic ratio. I forget exactly how that argument goes, but it appears to show that there must have been water bodies on the earth very early on. Well, the 129 xenon is the daughter isotope of iodine, which is a short-lived isotope. So this means that within 100 million years or even less, there should have been water on the earth. Zircons. I don't know exactly what zircons are. Maybe someone can explain it. But it seems to me to be evidence for bodies of liquid water on the earth that are also very old, as you can see. So there should have been oceans on the earth already at 4.3 to 4.4 gigayears ago, shortly after the formation of the moon. We should have had water oceans on the earth. Now, okay, that's an interesting piece of evidence, because it means that the earth must have acquired its water, at least a large part of the water, very early on. But it doesn't need to be endogenous just for that reason, because there is also an exogenous source predating this ocean, as we shall see, I think at least. Another argument that is interesting is that perhaps even if the temperature of the disk at the Earth's location perhaps was too high to condense water ice, maybe the gas molecules, the water molecules from the gas could have been absorbed onto the nebular grains. And some work has been done on that, apparently showing that this adsorption could have been efficient depending on the surface to volume ratio of the grains, that is, how fractal they are in their structure. So one could perhaps have acquired one Earth ocean at a temperature of 700 Kelvin if the surface to volume ratio was 100 times that of a sphere. Now, what shall we say about that? Do we know how fractal these grains were? What was the actual surface to volume ratio of real nebular grains? I don't think we know much, but this appears to be perhaps a possibility. What I would say against this is still this observed very simple fact that the asteroids of the inner belt seem to be very dry. If the Earth had been able to acquire a lot of water, why shouldn't the grains at that location have acquired a similar amount of water? So this is what I have against this idea. Shall we break for a quarter of an hour?
Yeah, sure.
Okay. Questions, perhaps?
How about the moon? I mean, if that was formed when the Earth was wet already,
Yeah.
did it bring any of this humidity?
The moon is very dry.
Very,
Yes. And that could perhaps be explained if we take into account that the moon formed from material that had been heated to, vaporized completely, and then accreted around the Earth. I don't know if if you could imagine that as the temperature fell, there could have been condensation of water vapor from this terrestrial material that would have been incorporated into the moon. But apparently the moon is very dry. And I tend to associate that with the very high energy of the giant impact and the strong heating of all the material that happened. But this is a big problem for understanding the origin of the Earth's water, because we shall see that the water likely came to Earth before the moon was formed. And then, when you had this giant impact, what happened with the water? The moon became very, very dry. So how could the Earth retain water? Well, maybe it could. This has to be studied. It hasn't been.
If it's keeping a lot of water in the mantle, then...
Yeah. I guess that the primordial atmosphere, which was probably water-rich, must have been lost. But water that already existed inside the Earth could have survived, probably. Must have survived.
But how clear is the evidence about the moon being very dry? I mean, there are speculations that there is.
We don't really know
on the moon.
We don't really know everything about that. Just that all the lunar rocks that were analyzed.
Yeah, but showing deeper down, of course, if anywhere.
Yes. Okay, we'll start again at 11.
May I have a question for the students?